SwayamPrabha. Digital India. Educated India.
What is a random variable? What is a discrete random variable? Continuous random variable? What is the expected value? The expected value is the mean, and then expected value of a function, the variance, and then I think we stopped up to covariance. Okay, the covariance is the correlation between two quantities x and y. Okay, so covariance of so normally we write it as covariance of x, COV of xy. Is basically the expectation of x minus mu x so is there an equation number for this? Can you tell me what is the equation number? The
13.
previous equation.
13.
This is 13. Okay. Okay. So where mu of x is the expectation of x. All right, so we can work on this further. So I'll just give you 3 minutes. I'll just, okay, 2 to 3 minutes. Just simplify this further. Latecomers who just logged in. We're starting with the covariance of two quantities x and y. I'm just trying to do some math. Just try to simplify this, whatever I've written. Yeah, can you do this? What are you getting?
Covariance of x and y is expectation of xy minus expectation of x into expectation of y.
Correct. So this is nothing but if it is a discrete variable, so you're going to get what's up? Is this okay? This is only for discrete variable. Okay. Did I make any mistake or is it okay? Is this okay?
Yes.
Yeah. Okay. Now, for those people who want to probe a little further, let's say last week, okay. Let's say minimum temperature in Delhi. Huh? Okay. Let's say share price of Reliance Industries. Okay. What do you expect the covariance of EY to be?
0.
Okay. Anand, are you there? All right. Is this clear? So that is the covariance. So there should be no connection between the minimum temperature in Delhi and the share price of Reliance. Okay. So, or the minimum temperature in Delhi and the petrol price of that day or something. So there should not be any correlation. All right. Okay. So this is as far as covariance. So covariance analysis can be done to establish if you have a lot of data, if you're a data scientist, a quick check would be a covariance analysis to check whether there is a dependence between the data. Okay. So if there is a dependence, it requires more investigation. If there is no dependence, you're fine. So you can come to the conclusion that they are actually independent. Okay. Or they're weakly correlated. All right. Okay. So it will be like this. So where is the covariance 0?
First one.
Okay. Of course, you can say why should it be like it can also be like this. Huh? This is also possible. Okay. Even then, the covariance is non-zero. It doesn't mean that when x increases, y has to increase. No need. When x increases, y can also decrease. It can also be non-linear, whatever. But
Sir.
the dependence.
Sir, but then in the first one, it is roughly a circle. How are we? I mean, what is the exact logic or math behind saying that the covariance is 0 in the first case?
It's not the math. Basically, you're trying to relate some two independent quantities. The math is your problem. Nobody asked you to relate the temperature in Delhi to the Reliance share price. You have so much of data. You believe in maths and statistics. You want to do something. So the data simply confirms that. Don't torture me. Is that okay?
Sir,
math is basically only our tool. Math is our slave. Okay. So math is below us. So our brain is more important than math. So it is telling you, don't try to correlate them. Don't try to force it and calculate some covariance. You're not supposed to do covariance with me. Is that okay? That's what it's saying.
Sir, but how are we supposed to derive that from a simple graph?
No, because there is no relationship. The So from a simple graph, for each value of x, there can be multiple values of y.
Oh, okay. So if one value of x,
Ah,
multiple y's.
ah.
relation.
For one value of x, there could be multiple values of y, or for one value of x, there could be multiple values of x, which means they're poorly correlated. Because the whole idea of science is to understand. You want to be able to predict. That is something which you cannot do if you get a covariant, if you get a plot like that, scatter plot. Is it okay? Is it okay? Hello? Hey, am I audible?
Yes, sir.
So,
Yes.
sir,
In the formula, so in the formula, shouldn't it be a double summation xi yj divided by n square? So if you're saying there are multiple values of y for a single value of x, so
No,
should
leave it.
do it?
No, let's not go into that. One at a time. You're asking multiple questions in the same question. Just wait. Relax. What is your first question? That some sigma.
The formula.
You're saying something.
Yes, sir. Yes, sir. Shouldn't it be a double summation xi yj
Where is it? Where is the double summation?
in the formula?
No double summations. Xy is a product. You're taking a sum of the product.
So, but then you said that there are multiple values of x for a given value of y.
No, that is for understanding. From the graph, I can say that. Don't link it to the maths. You just plot the temperature in Delhi versus the share price of Reliance. The covariance will tell you that there is some relationship. There is some logic. Using one, I can find the other. Don't link it to the formula and don't become a slave to the formula. Just from that plot, can you establish a relationship? No, right? It is all over the place. We say that plot is all over the place. There is no scientific relationship between x and y. Leave it. Now go to the original covariance as the way it is defined. Now tell me what is the double summation? What is the doubt you have? Split the two parts. Don't try to put something in your mind and get confused. That plot is not an outcome of that formula. That plot is a general common sense plot. Somebody who doesn't even know covariance is plotting. He's plotting some x versus some y. That covariance is a tool for us to understand things. That's all. It should not give us sleepless nights. Now proceed. What is bothering you?
No, it's fine.
Yeah. See, that's why sometimes the IIT students, even many students, if you have so many years of formal education, you go by the formula. The formula has to be. Formula is basically coming from an empirical observation. Formula comes much later. We should not become try our hands in front of the formula and say the formula. Change the formula. But the data of the temperature in Delhi and share price of Reliance is supreme. Your mathematics is subservient to that. It should help you solve the problem. It should not this reign supreme because it was first figured out covariance because somebody tried to study the relationship between two quantities. Please know that. Please note that if the covariance is a tool which is not helping us, we will ditch the covariance. We will go further. But we should be able to understand phenomenon, march forward. Okay? We should not swear by a formula or something which was derived earlier and then we live by it. Newton said something, it was followed. Then Einstein said, no, it is relativistic mechanics and this thing. No theory is so sacrosanct. Okay, everything will be washed away by time. Right now, covariance is a tool. That's all. Just give it only that much respect. Don't think that a formula which is written on the board, which is in a textbook, which is in JEE is coming is a gospel truth. Science progress because people ask questions. Nothing is so sacrosanct. You ask questions, you can find answers. All right. Now let's go to the normal distribution. See, since we are doing a lot of statistics, I was just looking at Amazon and I was trying to get a book which will give us the lives and times of Gauss. Okay, so I ordered a book by Trent, I think. Okay, so Gauss, the Prince of Mathematics. Okay, so it arrived on Saturday. It's a fantastic book. Okay, not very expensive, just a couple of hundreds. So he's only 15 years old, Gauss, right? So he's walking with his friend who is also aspiring to become a mathematician. He's telling his friend, okay, whenever I walk from the gymnasium, the school to my home, the number of steps, okay, I'm maintaining the same speed. I'm maintaining the same this thing, gait and this thing. But I always see that the number of steps from the number of steps from the school to my home is always changing. Okay, then if they have a discussion and this thing, and then next days they are discussing. Then the Gauss is telling his friend, if I plot it, it looks like there is some value which repeatedly I get, and there are other values which are close to this. But there are some values which I get on some days which are far away from this something called the central value. But these come very rarely. Okay, and then what is the exact distance between my school and the house? Because that is a difficult quantity to measure. Okay, then he says that his friend asked, "Is there a way of doing it?" Then he said, "Probably the exact distance between my school and the house must be kept as the unknown and the true value. Every day I am measuring from my steps and this thing. Every day I am measuring that minus that true value. I have to square it, and then I should find out the sum over all the days. Then I should find out what is it by if I randomly put that what is the true value. I should find out when that sum becomes a when that sum becomes a minimum. That place where the sum becomes the minimum should be the correct distance, should be the true value between my. See, this is how. Then we swear by the formula. This is how Gauss found it. This is how Gauss found it. So basically, it is a simply he's walking from the home, school to the home, school to his home. So this and all that y minus y square, all that you're asking me doubts. No, so is it n minus 1, n, this thing? Originally, you should find out why Gauss. How could somebody even think about this 200 years? He's just a 15-year-old kid. Okay. But turns out that Legendary had already proved it 10 years back. Gauss has not documented this. The original least squares, it doesn't, I think mathematics doesn't acknowledge that Gauss is the original inventor of this least squares principle. Okay. But still, this is documented in his biography. This is what so this book gives a lot of, this gives tremendous, the genius of Gauss is so evident in the book. You must try to read any of these books. Okay, so you can pick up Gauss or Newton, okay, or whoever scientist. Okay, you have a fancy for. Just look at the way they have thought about these things, and that's how they figured out. Okay, so it was very interesting this morning when I wake up very early. I saw this morning. So this is in some pages 40 to 50 or something of that book. It's a very nice book, very not much maths in that. And then how he figured out that root 2, why should root 2 be irrational and so many things. Okay, so infinite series and all that. So I think amazing guy. Okay, all right. Now, so look at this. So now when we write it as a formula on this thing, so Gauss originally tried to solve a practical problem, okay? And then that formula we are trying to apply for every situation. So I think the best way, Auguste Comte said that. I think when Auguste Comte, when he said, when he talked about how we should look at scientific progress, he said that in order to truly appreciate a science, you must know its history, okay? So if you look at the background, for example, it took several years. I mean, only now I'm beginning to think, okay, I am in heat transfer so many years. Why did this field develop? Why did it branch out of thermodynamics? Who were the first guys who said there should be a separate field called heat transfer? We have to set up a heat transfer lab. Some professor should work on it. What are the problems which a heat transfer professor should solve? So that's how one became many. Okay. Then originally started with natural philosophy. Then they said there's a mathematics, there's a physics, there is an astronomy, then there's a human body. So then came engineering, then electrical, mechanical. So it is amazing. All right. Anyway, now let's get back to the normal distribution. Okay. So The normal distribution is basically attributed to the great Gauss. He's called the prince of mathematics. Okay. It's also called the Gaussian distribution. So called Gauss 1809. Okay. So this is called the bell curve. Then plus 3 sigma minus 3 sigma. Okay. So this is the f of x is function is basically 1 by 2 root pi sigma square e to the power of minus half x minus 2 whole square by sigma square. Okay, what is equation number 16? Is it? This is f of x.
17, sir.
Okay. Huh?
17, sir. 17.
17. Okay, no problem. 17. Let's put the right number. 17 is very good. Okay. All right. So you can find out this maximum is how much? That is when x equal to mu. So this is correct. 1 by root pi. So this is this value. Okay. So now f of x is the distribution. Please note that f of x is the distribution. F of x is not the probability. The probability is given by x is the random variable. X is the random variable and x is the value it takes. My statement is very loaded. X is the random variable and x is the limit value it takes. The x random variable is capital X. The actual value, the limit where you're trying to find the probability is the small x. Capital X is the general random variable. Okay. So the probability minus infinity less than is given by okay minus infinity to x. Why should it? Why is? Let us write it properly. Integral minus infinity to x e the minus half here capital X should come minus mu divided by sigma whole. Okay. Okay. So this is given by, understand? What is that? That is this. X is the random variable. X is the random variable, capital X. Small x is the upper limit of the random variable. The lower limit of the random variable, if you take it from minus infinity, the area under the curve from minus infinity to that upper limit of small x is called the probability. Okay. Is the probability that a random variable x. Okay, you can note down. Can you want to write it down? You write it down. Equation 18. Okay, gives the probability. Equation 18 gives the probability that a random variable capital X with the mean mu under standard deviation sigma. I come again. Equation 18 gives the probability that a random variable capital X that has a mean mu under standard deviation sigma assumes a value between minus infinity and small x. I come again. One of the most important things you learn it right. The Gaussian distribution, the probability P is the probability that a random variable capital X with the mean mu with the standard deviation sigma assumes a value between minus infinity and x. That is what is the probability of finding that capital X to lie between minus infinity and this small x. Now you can have a normalized standard distribution, introducing a variable. I don't know, you want to call it zeta or z, whatever. Introducing a variable z. Now we can work on this further. Okay, again, I made the distinction. Capital Z is random variable minus mu by sigma. Small z, lowercase z, is the upper limit of x minus mu divided by sigma. Therefore, the probability of minus infinity less than equal to z less than equal to z, okay, equal to 1 by root of 2 pi minus infinity to z e the minus z squared by 2 dz. Okay, equation 19. Okay, all right. Now, often we are not interested in minus infinity to x and x to infinity and all that. We are interested in what is the probability between two limits. What is the probability that the capital X will lie between small x1 and small x2? Are you getting the point? What is the probability that this capital X random variable will lie between the two limits which are given by small x1 and small x2? I don't want to do this integration. It's a painful integration, e to the power of minus some square by 2 and all that. So these integrals are all worked out for various values of the standard normalized variable as well as the other variable. And these are available in the form of tables and charts. So one of the tables is given to you. It has been sent both on WhatsApp and also on email. So using that table, you'll be able to calculate. Okay. So I think your calculators and even program should have this automatically. Okay. So you can use this to calculate. Now, the key probability to be calculated is probability of x. Always you should say with mean mu. Variance sigma square. To assume a value between x1 and x2 is the probability of x with mean mu and variance sigma square to assume a value between x1 and x2 is x1 less than equal to x less than equal to x2. This is a very key probability in engineering terms. For example, I'm making a shaft for a car, for a transmission in a car, the axle shaft. The mean diameter is 75 mm. Okay, what is the probability that when I make thousands of shafts, the diameter is always lying between 73 and 77? What is the probability it lies between 74 and 76? Because this is used for my statistical quality control, and because this will have a bearing on the stresses and these things and so on. So when you're in manufacturing, when you're in a company, so not only for scientific computation, when you're in engineering, when you're doing some engineering, you have to know what is the probability of, because with that you will work out all your quality control parameters. Why do you want to do that? 100% inspection of a nut and bolt. Some Sundaram fasteners, TVS fasteners will make hundreds and thousands of nuts and bolts every day. It is not possible for them to fully test the dimension tolerance and this thing, check for everything. So they will take a sample, and so they have to use a lot of statistical principles to figure out that with certain amount of confidence they can say that this is the quality which we will give to the customer. Okay, so that is why statistical quality control is, total quality control is fine, but for these nuts and bolts, and is it worth doing all this for millions of nuts and bolts? I mean, that's fasteners. That's what you want to figure out. So you can use statistical principles intelligently to reduce your labor. At the same time, you can predict something with reasonable confidence. Okay, so this is P of less than equal to Z, right? Less than equal to. Did I write it properly? So please note, this is the critical formula. This is the killer. This is the killer formula. Okay, Z1. Did you say less than equal? Okay, less than equal to Z. So this is the killer. This is minus infinity less than equal to Z less than equal to Z2 minus, okay, P of. That's it. So what you have to do is, what is the probability that the shaft, which has a mean of 75 and a standard deviation of blah blah, diameter lies between 73 and 77. So you have to find out probability from minus infinity to 77, probability from minus infinity to 73. Get the difference. So the first will be area under the curve from left to right. You put it like this. And the second will be from area of the curve from left to right up to that D2 or whatever. Then the difference is actually the answer. So this, if you want, you can calculate using a program or whatever. It's directly available in the form of charts. Okay. Why is this such a big deal? Okay. So this is 20. Very, very good formula. For those of you who are formula bucks, okay, you will die. You will swear by formula. You think that formula is God. With those people, it is very useful because it helps you calculate many things. All right. So the Gaussian probability is very useful in engineering because it lets us estimate the confidence interval between estimates. Are getting the point? Coming back to that diameter, with how much confidence can you say that 99% of the time, or if I want to say with 99% confidence, what are the limits of the diameter of the shaft? Or alternatively, okay, with how much confidence can I say that it will always lie between 74 and 76? With how much confidence can I say it will always lie between 74.5 and 75.5? With how much confidence can I always say that it will vary between 71 and 79? With how much confidence can I say it varies between 0 and infinity, that is 100% confidence? But the thing is, you want to say it more accurately, but whenever you bring down that interval of uncertainty, then obviously your confidence level will go down. So, but the confidence level can be only as good as the process. Okay, forget about the data, forget about the max, forget about theorem, forget about Gauss. What is the manufacturing process you are using to make the shaft? How much tolerance and accuracy your machine will afford? Then there is a human error in the measurement. There is human error in the calibration. Okay, so there is a natural variability. So regardless of your high funda statistics, it cannot get past. Okay, the data is only as good as the model. That's what we keep saying always in scientific parlance. The data cannot get past the model. It's only as good as the model because the model was used to generate the data. All right, and if you measure the accuracy of your measurement is only as good as the accuracy of the thermocouple. Therefore, you should know your limits. We should know the limits under which we are operating, whether you're doing simulations, modeling, or whether you're making measurements. All right. Now, let's solve some nice problems. Tell me the problem number. Problem number, next one.
Second one, sir. Second one.
Only the second one.
I think excluding the first example, it is the second one. Otherwise, it's the third one.
Okay, so let's say some 3. Who is this? Who's talking?
Harshini, sir.
Okay, very good. Okay, you are saying 3. Let's believe. Okay. Let us believe. Faith is important in life. As one philosopher said, life without faith is impossible. So we will believe that 3 is right. Rajesh Akula. Oh, that first one is a long example. That's why it is still question number 2. Right. So maybe I have it on the PPT, but it's no fun. Okay, I will dictate. Let's, all right. Okay. The annual rainfall in a city. Okay, this problem is about annual rainfall in a city. Let's say it's like Chennai. Annual rainfall in a city follows a Gaussian. First, I have to say that the annual rainfall in a city is normally distributed. Okay. The mean is 900 millimeters a year. It's annual, so I don't have to say per year. And sigma is 250 mm. Is that okay? So this will be like typical, maybe Chennai. Chennai has got a high rainfall, but it also has a high variability. I'm not saying this Chennai data, don't quote me. A city like Chennai, where we get 100 centimeter, a meter of rainfall every year, and a lot of variability. Last year there was Ajar rainfall, and 3 years back there was no rainfall, 50% rainfall, and so on. Let's say that the annual rainfall in a city, the annual rainfall in a city is normally distributed with a mean of 900 millimeter and a standard deviation of 250 millimeter. Okay, full stop. A. What is the probability that the annual precipitation will be more than 1200 millimeter? He's fine. So the first quiz will have some problems on Gaussian distribution. So we'll give 1 or 2 tricky questions also. So it's good if you attend the classes and try to solve the problems. Okay, it will be useful. Dear all, please send your roll numbers. Akula is saying something. Okay, just look at your chat box. No, hey Ujjal, you want to come on the?
Yes, sir.
Yeah. So show your face. So
Yes,
other
sir.
guys, you can just pin this video if you want. Ujjal.
Yes, sir.
There you are. Okay. You seem to be very happy today. It's good because everybody is suffering
Yes,
from
sir.
lockdown blues. Yes, tell me. Let's do the steps, Ujjal. Let's go ahead. Tell me.
Sir, we can convert it into small z. This is in x.
Small
We'll
z.
convert it. Is the
X equal
variable
to?
1200 minus 900 divided by 250.
Very good. How much is it?
It's 1.2.
1.2. Okay. So we have to say probability of
Z less than 1.2. Z greater than 1.2 equal to 1 minus probability Z less than 1.2.
very good.
And
what is
Z
the probability less than?
0.8849.
Okay, as a percentage, what will you tell, Atul? As a Ujjal, as a percentage, what is the chance that the rainfall will exceed 11.51%?
11.5%.
11.5%. Okay. Okay. So let us have some more fun. So you're having the tables right there, no? Ujjal?
Yes, sir. Yes, sir.
Okay. Okay. Let me do something. So you're ready for the challenge?
Yes, sir.
Huh? Oh, very good.
Yes, sir.
That's the spirit. Okay. Now work out the probability, the class, work out the probability 2b. Ujjal, note down.
Yes, sir.
That the probability is either less than 750 millimeter. Get the probability that the annual rainfall is either less than 750 millimeter or more than 1200 millimeter. Ujjal, got it? Others also? Come again. What is the probability that the rainfall is either less than 750 millimeter or it's more than 1200 millimeter? It has got two parts and one part we already saw. I'm saying either or. Okay. Okay. Ujjal, funda number
sir.
1.
Yes, sir.
If it is either or, you will get two probabilities. What do you do with the probabilities?
We'll add, sir.
Exactly. Excellent. We'll add. So work out P1. P2 is already known to you. And then P1 plus P2, then we close the class. We'll continue tomorrow.
80%.
Array, you're very fast, man. What is that?
80.66%.
You already know the question even before I ask.
No, sir. I've seen the 69.15. I added with 11.51.
750. Come again. What is the funda you used?
So 69.15% is for the less than 750.
Oh, very
For
good. Very good. You are
0.5.
very fast.
So
Very good. Very good. Let us work out. Wait. Now, probability of x.
yes, sir.
Agreed? Already got this. Agreed? So, P2. Ujjal, please. Again, Z. Z equals
Z is equal to 0.5.
750 minus
7. Oh,
Minus 0.6.
Minus 0.6, sir.
I did
So-
wrong actually.
you did wrong. 750 minus
900.
1200.
900.
30.85.
No. 900.
42.36%.
Divided by 250.
Parshini, tell me. Z.
Minus 0.6, sir.
Minus
Minus
0.05. So minus 0.5.
Oh, what?
0.6, sir.
Minus 0.6.
Minus
Is correct?
0.6.
Now, probability of less than
Minus
0.6.
minus 0.6. How much?
0.2743.
0.2743.
How much is it? 40%.
3894. 0.38.
0.3894.
Around 40% chance. Okay. Okay, so now I can keep on torturing you further. Okay, so we can say that sigma is 250 and the mean is 900. So 3 sigma is 750. So watch my arguments very carefully. Mean is 900, sigma is 250. So 3 sigma is 750. So 900 plus 750 is 1650. So if you work out the probability of the rainfall exceeding 1650, what should you get? What is the probability of rainfall exceeding 1650?
0.03% or something.
0.15%.
That whatever. So it is that 6 sigma G company, 6 sigma green belt, black belt, all that they said. No? So this is, I am telling you, mu plus 3 sigma. So it will be in the tail. So this is in the tail of the curve. Is it okay? So this is also the problem with the Gaussian. So you are thinking that some of us are very this thing of Gaussian. What happens with the original distribution itself is not normal. It's quite possible. Okay. Who tells us that all the phenomena have to form a normal distribution? It is normal. Sometimes things can be abnormal also. Therefore, there should be a way of dealing with abnormal distribution. So extreme value distributions and so on. So all these mathematics, all these are a construct. They help us solve a certain level of problem. For example, nobody could predict the pandemic. Okay, but Taleb, okay, the black swan. I mean, the author of this black swan. You know Taleb, the professor. Okay, Taleb, whatever you want to call. He said many years back, there may be some disease which will affect the whole world, which means spreading aircraft and all that. He wrote some 10 years back itself. He is the proponent of this black swan. Okay. So suppose you see a swan. Swans are generally white color. Okay. So today you see one swan, it's white color. Tomorrow you see a white color. Fourth day, fifth day, fifth. So even if you take 100,000 data points and now you've got a full data science, your full data science says that all the swans are black. Therefore, if you come to the conclusion that so far I have seen only white swans, okay, and it is built with big data, then you will come to the conclusion all swans are white. He says one black swan is enough to completely destroy the hypothesis. Okay, the collapse, the economy collapse of 2000, Lehman Brothers, whatever, the corona pandemic, okay, the tsunami of 2000. These are all black swan events. So data science, Gaussian distribution, all this can be used only to, it cannot. So it requires certain kinds of tools. It requires certain other kinds of tools to figure out all these things. So he said that, so that, and also if somebody is keeping a turkey in his house, okay, every day is giving food. What is that idea? One day when it becomes big, he'll kill it and eat it for his food. Now every day the turkey is getting that food. It is having a reinforcement learning. This fellow loves me. Every day after day he is giving me food. Therefore, he will never kill me. That is a wrong hypothesis, because the whole killing is the whole idea of giving food is so that it becomes healthy and big that one day. So regardless of the number of days it is given food, it can be killed one day. So he says that in a situation like this, we should not become the turkey. Okay. So please read his books. So he is a great probabilist. Okay, Taleb. So Black Swan and all that. So he's written other books also. Okay, Skin in the Game and all that. All right. So if I have some free time, I'll talk about his works. It's all scientific. Okay. So all right. So you can just Google it up. And so tomorrow we meet at 10 o'clock. Thank you.